because according to Nathan, it's the time that the internet goes on, so we're transmitting live. Thank you very much for joining us this evening for the annual alumni lecture. Welcome to the University of Vienna Department of Chemistry. We're an institution that's very proud of the research that we do here, and after Professor Reisner's presentation, you'll see why it is that my colleagues do the work that makes us one of the world's great chemistry departments. We're very proud that even in the University of Cambridge, which is considered one of the world's great research departments, the chemistry department here is considered most probably one of the strongest research and teaching departments even within this university. And we're extremely proud of the work, extremely proud of our colleagues like Erwin and also some of the PhDs that you'll meet tonight. Some formalities, some housekeeping. We don't expect a fire drill to go off this evening. If it does go off, please follow the yellow signs out of the building, which lead us either to Union Road or the top of the ramp at the bottom. You'll see a lot of other people running, so just follow them. And what we'll do is we'll meet in the car park end of the building. The toilets are just outside the front of the cyber cafe here. The team can also lead you out. If you do need to leave early for any reason, the team will lead you out so you don't get lost. It's a big, complex department. If you take a wrong turn, you may be here next week. And also the car park barrier will be open at the end of the event so that you can leave, and someone will be there to help you out. A couple of thank yous. Thanks to Erwin's members of the research group that are here to make the event more interactive and enjoyable. But also thanks to Diane, Caroline, and Chloe, who've been fantastic at putting this event together and making sure that you're here, and to Nathan and Michael, who are projecting this to the world. So Erwin is one of our real stars. He has a career that's really brought him all over the world. He started off in Vienna, then via MIT and Oxford, two very, very fine institutions. He worked his way up to the best of the three, which is to come here to Cambridge via Manchester. He came in 2010, I realize. Is that correct? It seemed like only yesterday, but it was quite a while. And he rose through the ranks very quickly to become Professor of Sustainability and Energy. He has won numerous grants, many prizes, including the Hughes Medal only a couple of weeks ago. The work that he and his research do is truly world-class. I, even myself, when I did research, would like to think that what I did was important. That's what gets us out of bed in the morning. The work that Erwin does is important. It's important to all of us. It looks at sustainability in the way that we deal with new generations of materials, and the work that he will present, I think, is really awe-inspiring. So we're really grateful that he's made the time to present his work today. And there may even be some experiments to show, which is absolutely fantastic. Sit back, enjoy what I think will be a tour de force, and then there'll be an opportunity for questions and answers at the end. Erwin, up to you.
Thanks a lot, Nick, for the very kind introduction. It's a real pleasure to be here, so I really welcome you all to the chemistry department. And I will not be the only one presenting, so I would really introduce as well Motia Rahaman, Virgil Andre, Suvendu Karak, and Celine Jung. All of them play a very important role in this presentation, either as presenter or as demonstrators at the end of this session. So what we would like to present to you is really our ideas, our vision on some prototypes to enable sustainable chemistry, to enable a sustainable future powered by sunlight. And I would like to introduce why we think solar energy is important. I hope this will be an easy case. I would like to introduce to you the challenges we face with fuels and how to make circular chemistry a reality. And then I'd really like to talk about artificial photosynthesis and how we can actually really use sunlight to power chemistry. So to introduce solar energy, you're all familiar with solar panels. They produce electricity. We see them on our roofs and everywhere emerging, and that's brilliant development. But there's one issue when it comes to electricity. It really is only a small part of the global power consumption. So if we look at the global power demand of about 20 terawatts, only about 4 terawatts are really electricity. So this is maybe 20 or 25%. So while it's very important that we roll out solar technology, wind technology, hydroelectric technologies, in brackets, nuclear, maybe not sure, technologies, we still lack 75 or 80%. And this is really being provided in the form of fuels. And of course, today these are fossil fuels. So we need urgently ways to make these fuels sustainable. And this is a challenge that has been barely touched upon. And we try to address this limitation. And the idea is really, can we build something like a solar panel that does not generate electricity, but that may make your gasoline, your kerosene, and your chemicals, your pharmaceuticals, and your materials for the future. Why do I think solar energy is the way forward? When I started my research group, as Nick said, I moved here in 2010. The case for solar was more an idealistic one. It was much less an economic one. So if we look at this plot with only 2 time points, 2009 and 2019, you can see that photovoltaics was very expensive. And what I'm plotting here is the cost of electricity from those technologies, expressed as levelized cost of energy in US dollar per megawatt hour. This means the cost of the electricity if you were to build a plant today and let it run until the end of the lifetime, not taking into account storage, transport, etc. But it's still a relatively fair metric, I think, to compare energy. The incumbents, the fossils, coal, gas, quite unchanged in the 10 years. Wind had quite a remarkable development, actually beating the fossils in most scenarios, and certainly in the UK, extremely attractive. But not even the most optimists actually predicted what would happen to photovoltaics. And you can see that photovoltaics today is certainly among, if not the cheapest form of electricity. So in an unsubsidized way, it does beat fossils already. And you will also see these numbers are from 2019. I think we know what happens to fossils. They did not become cheaper in the last few years, whereas solar actually did keep dropping down. And I think it sits now by about $35. So it is a real market advantage. This means solar is already abundant and cheap. And solar benefits from a learning rate of 20%. What do I mean with learning rate of 20%? If you double capacity of installation, you drop the price by 20%. So it's the economy of scale which has actually enabled this drop, and it keeps dropping. But there will be a saturation scenario when we have enough electricity. And in several countries, there are already peak electricity situations, and we need to start to think about storage, seasonal storage, and at some point we need to make these fuels and chemicals sustainable. And so I really believe, even from an economic investment point of view, future growth of solar will be through chemistry. If it's what I'm showing today or not, I don't know, but this will become a very, very important way forward. So what does all of this mean? What do actually we do with all these fuels? Of course, we know we need it for our cars, we need it for aviation, etc. But we should not forget of the huge chemical sector that powers our daily lives. What I'm showing here is what I like to call the organic chemistry of the fossil age, of yesterday. Fossil fuels as a resource, we derive base chemicals. It's actually quite a small portfolio. Things like ammonia, syngas, methanol, aromatics, ethylene. And from those we derive all our products that we use in our daily lives. And of course, all the uses. So if we just take one example, we take natural gas. We steam reform natural gas to make hydrogen. This hydrogen we use in the Haber-Bosch process to make ammonia. And this ammonia we use to produce fertilizer for food. 50% of all your nitrogen in your body was produced from the Haber-Bosch process, which is powered by fossil fuels. So in fact, we do not even have enough fertilizer to sustain food production in a sustainable manner to maintain global population. So there are many, many problems interlinked with fuels and sustainability. And I could go on and on. And 99% of all the chemicals we are using are also not sustainable. But really, what do we need to do? And what I think is relatively frightening, we have actually, if we are serious to meet 2050 targets, we have less than 27 years to do this on a global scale. We have to transition, phase out fossils, and to replace it by sustainable resources. I will introduce in a second what I mean with those. And of course, we want to keep our products and uses. If anything, we want to expand those. So this is a massive shift going from a fossil to a post-fossil age and a sustainable future. And the tricky part is, of course, if we have the resources, how do we make these feedstocks to power all of the chemistry, to source all the commodities and fuels that we need? And we believe that solar, again, can be the energy input to drive this chemistry. So what's the scenario I'm interested in? And I show this here as an illustration with the chemistry department. You should recognize Lansfield Road chemistry. The first action I would suggest is we get rid of the car park Not popular by many in the department, but I think this is a way forward. And we install some solar chemistry panels, how we call them. And these panels convert our waste and resources into useful chemical building blocks. So we can take water. We're very interested in polluted and seawater as well, not just fresh water. Components from air, so for example sourcing, and we will present today how we can use the greenhouse gas carbon dioxide as a feedstock for carbon or organic chemistry. Nitrogen from air is also very attractive to make maybe fertilizer in the future sustainable. And anything waste, anything you would put in your blue or green bin, that's biomass, for example. We like specifically lignocellulosic biomass because it's not in competition with agriculture. So there's no farming issue at all. We only want to have the waste from the farming industry. And we have an interest in plastic pollution as well. Can we use plastic waste as a resource to build future chemistry in this case? So if we make this a reality, then we talk to Downing College, taking over their site and build some solar factories here to make our synthetic fuels, our kerosene I mentioned, our chemicals, our pharma products, our materials, plastics, fertilizers, steel, hopefully, of course, in a sustainable manner. This directly addresses the question of energy storage. If we can make liquid energy carriers, and we will also talk about this today, then we can store them, we can transport them, and ultimately we can use them for our vehicles. Aviation in particular, heavy transport is particularly attractive. And last but not least, for seasonal storage, we can even convert it back to electricity to make sure the light stays on in the chemistry department. So it's a circular chemistry approach to what we try to do. We do basic science, but actually we like to think very much about translational research and real-world problems. So as an illustration, I just show one picture of a subgroup from my team that are interested in plastic conversion in particular. And our first excursion after the COVID pandemic was actually to go to a waste recycling facility. Some people would have gone to the Caribbean. We go to source some waste. And this is actually from RECAP, so the Peterborough Cambridge Waste Recycling Partnership at the EMI facility. All local children actually go to this facility, which I think is really good. And what you can see here at the back is a mountain of non-recyclable plastic waste that will go to incineration from a weekend in Cambridge. What did surprise me was maybe not so much the size of the mountain, but actually when you go there, the composition, because you will find a lot of plastics there where you're told it's recyclable. PET is one example, which is the most prominent for recycling, but even PET, if it's contaminated with food, if the machines can't separate it, if there's a mixed plastic composition, it will just be incinerated. So it remains a massive problem where we hopefully find some solutions. Okay, so what we'll be presenting today, it is really the idea of taking solar panels to do chemistry. Can we take such a panel, put it into a reactor with water or seawater, with our waste, shine light and make something useful out of this? And the approach we take is really known as artificial photosynthesis. What do I mean by this? We look at nature, we look at leaves, and how do they function? How do they make sustainable energy carriers like glucose? They take water, they take carbon dioxide, they take light, and then they make the sugar. And we're doing something very similar, just we are not interested in sugar, because it's not just a useful chemical for us. We try to make more interesting building blocks. And the starting point here was really an outcome of a 7-year center we had here in the department, where we could demonstrate the conversion of carbon dioxide, the greenhouse gas plus water, with sunlight into what's known as SynGas. SynGas is a gas mixture of carbon monoxide and hydrogen. Sounds horrible because CO is toxic, but this is really useful, believe me, in the chemical industry. And we produce already SynGas on a hundreds of megaton scale, but just from fossil fuels. So if we could make SynGas sustainably, we could actually just cut fossil fuels out of the petrochemical industry. And that's what we can do, plus oxygen. And the SynGas you can then use to make these fuels, chemical, plastics, etc., that I've discussed before. So this is just one example. And since I mentioned artificial photosynthesis, we also like devices that look like a leaf. And here we term these artificial leaves. That's one example we'd like to introduce today. You can see it here. And these are even so light and thin that if you put them in an aqueous solution with CO2 and shine light, indeed they produce SynGas and actually levitate to the water surface. And this I'm showing because it's actually quite good fun to use this thing on the River Cam. So actually we took one of those, we made a bit of a larger one, put it into a plastic bag that's sealed with water and carbon dioxide and could convert carbon dioxide from the bag with water into syngas in this particular illustration. And since it's floating, we call this an artificial lotus leaf. The person who really assembled all of the first demonstrator here is Virgil Andre. He will present in a moment. And he really showed the conversion of carbon dioxide to syngas. And you can see the time scale. This is all quite recent. So this is actually, the results really came and were disseminated in the COVID pandemic. Since we had not more to do, I guess, in the lab than really work on this, we were busy. Esther expanded this quite quickly from CO2 to formic acid. Formic acid is a C1 carrier. It's attractive because it's now a liquid energy carrier. So carbon monoxide is a gas, formic acid is a liquid. Motya Rahman, who will also present in a moment, showed that we can take carbon dioxide actually to more complex products with carbon-carbon bonds. So ethanol, for example, or even propanol. So again, very attractive fuels for storage. Sayan Kar showed we can actually take carbon dioxide directly from air by coupling our technology with direct air capture technologies. We do not rely on concentrated CO2 streams. And Subhajit Bhattacharjee showed that we can also use waste in the form of biomass and plastics to break down plastics to make interesting chemicals. I have no time today to talk about this at all, but I will just show a little bit what we can do with carbon dioxide. And this, and here I really like to hand over to Motya Rahman, who will introduce how this artificial actually works.
Thanks, Erwin. Welcome everyone to the event. So, we are talking about artificial leaf. So, why we call it artificial leaf? Because it mimics the working principle of a natural leaf. So, the natural leaf takes carbon dioxide from the atmosphere, it takes water. Using sunlight, it converts carbon dioxide and water into sugar and releases oxygen. Our artificial leaf, it also uses carbon dioxide, uses water, sunlight as an energy source. Instead of sugar, it makes chemicals and fuels, and also releases oxygen. Now, the artificial leaf, it's a device, and it has two key components. One, it's light absorber, which actually absorbs sunlight and converts it into photovoltaic. The second key component is the catalyst. So the catalyst is something that accelerates a chemical transformation. So we can see here a sandwich type of assembly. It's an example of one of our artificial leaf. It's a sandwich type of assembly of different sets of light absorber and catalyst material that actually does carbon dioxide conversion and water oxidation. So it actually simultaneously converts carbon dioxide into chemicals and fuels and does water oxidation into oxygen. Well, in the next couple of slides, I'm going to talk more about the carbon dioxide converting catalyst. There are different types of catalyst material that can convert carbon dioxide into fuels and chemicals, like molecular complex, like biological catalyst, or even metal oxide, metal alloy type of catalyst. The metal alloy catalyst, they're actually robust, selective, and easily scalable catalyst material. And how do we prepare those catalysts? So there are, again, different procedure to prepare those metal catalyst system, and we use a novel electrochemical approach to prepare the metal catalyst. Here, we use a support. It's a kind of a metal foil we can use. Here in the picture, you can see it's a copper foil. And then, depending on our requirement, if we want to use a monometallic, if we want to make a monometallic catalyst or a bimetallic catalyst, we have to use metal ions. We can see here a deposition bath. It contains metal ions, and then the support is submerged in the solution. Using electrical energy, we convert the metal ions into corresponding metal form. So if we use, let's say, if we want to make a bimetallic catalyst, we need to use a combination of two different metal ions. So they will co-deposit on the substrate as catalyst. We can see here the dark brown part is the deposited catalyst. It's a bimetallic catalyst. We used two different metal ions. Now, how does a catalyst actually look like? We use a very strong, a powerful camera to use it, to look at the morphology of the catalyst. It's called electron microscope. If we use electron microscope, we can see the catalysts, they're actually macroporous. We can see some nice porous structure. The pore diameters are around 30 to 50 micrometer. That's similar to a diameter of a human hair. Even if we zoom in there on the side wall of the pore, we can see some nice dendritic branch nanostructure. So here I'm showing an example of copper indium catalyst. It's a bimetallic alloy, copper indium catalyst material. If we use this catalyst for carbon dioxide conversion, this catalyst actually, it can convert carbon dioxide and water into syngas. As Erwin mentioned, syngas can be further converted into some useful chemicals and fuels by a second step. So it's a really, really useful product. Well, so we need a second step to get direct fuel out of this. But if we want to get direct fuel from carbon dioxide, what to do? We can change the catalyst system. If we change indium to palladium, if we can make a copper palladium system, again, we can achieve this macroporous structure, dendritic nanostructure. The scenario, the performance is completely different here. Now we can see this catalyst, it can directly convert carbon dioxide and water into multi-carbon alcohol. So we can get ethanol or propanol, which are high energy density liquid fuels. They're drop-in fuels. We can use them in car. So changing the composition or morphology, we can actually direct the selectivity of carbon dioxide conversion into different products according to our need. So the catalyst is really an important component in our artificial leaf. And we assemble this catalyst, we attach this catalyst to the light absorber, and then to make or to assemble our artificial leaf system. My colleague Virgil Andre will talk more about the light absorber systems and their assembly. Virgil.
Okay, thank you, Motjar. Okay, so as we were saying, plants use this process called artificial photosynthesis to convert small molecules like water or carbon dioxide into fuels. Our artificial leaves are inspired by these natural leaves. So in this case, we also want to use two light absorbers that will use different parts of the solar spectrum. And that means, for example, we are going to take this yellow-greenish light absorber called bismuth vanadate to oxidize water and to produce oxygen. And we will take this other darker light absorber called perovskite to do, for instance, CO2 reduction. Now, as you can see, this light absorber, the perovskite, is very dark. And this is really good, because it means you can really harvest a large chunk of the solar spectrum. And this is one of the reasons why perovskite has become a very popular material for solar cells over the past decade. And you can see here the increase in efficiency for solar cells. It's now almost surpassing that of commercial silicon solar cells, the ones that you put on your rooftop. Now, there is a catch with this perovskite. And that is the fact that if you dip it in water, it will degrade within seconds. Okay, so then how are we going to use this material that degrades within seconds in an artificial leaf that we will actually dip into water? And so to do that, we had to think of a way to protect this light absorber. And so we need a material which is ideally inexpensive, earth abundant, something that will keep the moisture out, but also something that will let the charges, the electrons, go through to the surface. So what could that be? Well, let's think of something that each of us has access to, that you can find on every desk, that you can find in every pencil. And that is graphite. And we will have a demonstration on this later. And so we took powder of this graphite, we used it to make a paste, and then we coated this light absorber with the graphite. And so what happened now was that these artificial leaves were able to withstand the solution and to work in water for multiple days. Now, this material is also quite versatile. And that means that now we could, for instance, use it to reshape our entire device structure, and from this type of bulkier panel to go to this very thin type of leaf. Now, you can also do more things with this material. You can use it to easily coat a larger area. And this is what we did here. We showed that we can, in principle, make larger devices. And this is quite important because most devices, most prototypes that we typically test in the lab are quite small. Whereas we really want to take our technology further, and we really want to push towards real-world applications. And so this was one of the directions that we have been working on over the past few years. And here I just want to show you the steps of development. So we started in 2020 with these artificial leaves, devices that were roughly 10 square centimeters in size. Then in 2022, we managed to introduce these lighter, flexible devices, the floating leaves, that are 100 square centimeters. And right now, we are able to make these arrays of devices, what we would call, let's say, an artificial tree. And, well, making devices larger is one thing, but you also need to house them in some sort of a box, right? To collect the gases, to collect the products, and to use them. And so one important part of our work has been also developing different types of reactors for these leaves. And so you can use these transparent plastic plates to build these boxes, or you could also use 3D printing, which is quite nice because you can basically design your reactor in one day, and you can let it print overnight. So you can test much more configuration, much more reactors with this. Okay, so now I will hand this back to Erwin, who is going to talk about these experiments.
So thank you very much, Virgil. There was another reason why we built this artificial tree or this larger device. And the reason is that the European Commission around 2016, 2017 announced a big competition and a prize for solar fuels, for taking sunlight and making fuels from carbon dioxide. And it was announced, and more than 20 teams essentially applied, and a few of those were selected for the final last year in Italy. This was here in July, where this picture of the team here was taken. And you can see the team. It's Virgil, me, and Motia from our group. And we work together with Sam Stranks, who is a professor in chemical engineering, and his team members, Miguel and Yuxian here. And we built this device, and again, the competition was 3 days of demonstrations to convert carbon dioxide with sunlight into a product, and there was a bunch of different criteria who would win the prize ultimately. It was quite an experience. The deadline was very sharp. COVID didn't help, of course, with the deliverables and assembling the device, but we just managed. You can see here we drove down a car. We crossed the Eurotunnel with many issues with customs. There's now a much more harder border than in the past. We noticed that. And it was a long drive towards Italy. But we made it. We brought all the device safely there, and we were ready to go. This is what I would call our official snapshot before the device started. As you would expect, blue sky, everything seemed ready to go. But unfortunately, things turned a bit sour. And on day one of the competition, the thunder clouds started to come in. And in fact, this was the first day really where we had immediately to cover the device. It was such heavy rainfall and wind that effectively we could not really operate our device. And in fact, on this one day, on day one of the competition, 1/4 of the annual rainfall came down in this specific location in Ispra in Italy. And you can see here in this video as well, not sure if you can see, but it was really pouring very, very heavily. And this was a bit unfortunate actually for our competition, because what we had intended to do was to look at different device scales from a small to a mid and what we would call our larger reactor. And of course we've tested our device, but we only tested our device in the UK when the sun was out. So whenever it was sunny, we ran out and tested under real conditions and it worked. And one very important aspect for our device was actually it needed, if you like to switch it on, it actually starts producing our product SynGas, and we build up an overpressure. And this overpressure would then actually pump the gas into a reactor or into a container where we collect our product. And because it was raining the whole first day, our device never switched on. And in fact, it went into reverse. We started building up some underpressure because the CO2 still equilibrated with the solution. And this, unfortunately, we had some leakage and some backflow from one of these containers. And this valve is the culprit. Yeah, so next time we've learned that lesson. And the consequences were quite dire. So this is our functional device. And we know if our device is working just by looking at it. So we need to see this yellow color from one of the light absorbers that Virgil introduced, the bisosvenadate. And through this back flux, you can see we got a basic solution into our device. We changed the pH value, and we started to dissolve, unfortunately, our artificial leaves, so which was a bit of a tragedy in this case. Nevertheless, we finished second place. Very proudly, I have to say, we were the only team that could actually demonstrate direct CO2 conversion. But unfortunately, due to the breakage of the device, we could not really produce much fuel because our leaves were dead. You can see the medal, which we proudly received. The trophy is actually also here on display. But if you look very closely, it's not this endless happiness that you may expect. And the reason is because there was no other prize associated with the second prize. There was no, well, we were waiting for a check, but there was no check. But what do you think the first prize was? Money. 5 million euros. So it's money. It's money. It's money. So yes. So we when we talk to students, or when I talk to students as well, and there's something difficult, we say it's a character building exercise. I think in this occasion it's character building for us, and we will learn from this. And next time we'll be back and bring it home. Is that the consensus? Yes. Okay. So this was the competition. What we wanted to show is just really what do we do, what's the idea, and just show a couple of prototype systems. What does excite me is the pace of development. So this here was the first standalone device we had in the laboratory, 2012. It did make some traces of hydrogen. Efficiency was very low, and it just fell apart within half an hour. There was not much more we could do, but we were excited, at least it worked. This is also on display here. So you can see the evolution of some of the devices from the group. Whereas today, we can really manufacture this in all sorts of different forms. So we can integrate all of this into essentially a millimeter device that's far more efficient. They can do far more chemistry. They can really break down the waste. They can convert carbon dioxide. We have quite some versatility of products we can make. And of course, also we can build larger arrays. And the next time we make sure the valve is also tight and there's no associated problems. So with this being said, I will now hand over to Celine. And Celine will a little bit present what we do on outreach and public engagement.
Thank you, Erwin. Now for something a bit more lighthearted. We are actually a very fun group to be in. And even though we work really hard in the lab, outside the lab, we love engaging the Cambridge community, which is all of you, with multiple outreach events. And this year, we were really lucky to host more than 100 students from Parkside Community College in our own Wilson Lecture Theatre It was really a fun-filled morning with lots of experiments. And yeah, there's me, Carolina, and Tessel with the hydrogen cars. It was also really nice for Erwin to provide some career advice and the educational pathway towards a PhD, which is something I wished I had when I was a high school student. And we were also there at the Chemistry Open Day in the iconic yellow T-shirts, and of course, everyone was really happy. But besides, within the department, we also made the trip out to Newham Croft Primary School to introduce to primary school students the concept of artificial photosynthesis and to really get them started about thinking about renewable solar energy. And at this point, I would like to take the opportunity to invite you to join us at next year's Cambridge Festival. So from exploding hydrogen balloons, boom. No, it should boom. Okay, great. And to solar-powered hydrogen cars, and of course, photocatalysis experiments. I promise it's really going to be fun, so do mark your calendars at 16th of March next year. And at the same time, we are really active on social media. We have Twitter, or you would call it X for now, complicated issues. But we also have our own dedicated website for outreach events. We update it regularly with pictures and videos, so do check it out. And today, I would like to just introduce a very simple and fun experiment that you can do at home. The kids really love it. Every time, they would just, can I touch the bubbles? Or, can I do something with it? So it's really fun. So what you need, what it is actually is to do water splitting. And what you need is just 2 graphite pencils and connect it to a battery or a solar panel. And you would just produce hydrogen and oxygen bubbles on both ends. And what's really nice is that you can have red cabbage. I really bought them from Sainsbury's. It's here. Out for grabs, it's free. So red cabbage can serve as a pH indicator to really track the pH changes at the cathode and the anode with time. And it's a really fun experiment. But in the interest of time, I'm not explaining the whole detail as of now. You're more than welcome to pop by the bench, and we can have a nice chat, be it on the experiment or what's life as a PhD student in the lab or as a down in college student. You're more than welcome to come and chat. And from a broader perspective, it's more on the research in our group tries to move beyond the traditional PV electrolysis or battery electrolysis system that is in this experiment here, and really combine both light absorber and the catalyst in a single compact device. And with that concept in mind, I would like to pass the microphone back to Erwin.
Thank you, Celine. And we're already coming to an end of the presentation, so I'd really like to thank, of course, all my co-presenters very much. Everyone from the research group, we could only present a very small part, just to give you an idea. Of course, you for your attendance, all the funding bodies, also the collaborators. We collaborate quite heavily within Cambridge with other departments. And of course, everyone who made this a reality. So also Diane and her team, everyone, really a huge thanks. And I think depending on Nick's plans, we probably have time for a couple of questions. And I'd also like to invite you after the questions to come actually to the table. We have, as I mentioned before, we have some outreach experiments prepared. And we also have a couple of demonstrations from the very early stage devices to the larger and more modern type of systems we are exploring. And Suvendu Karak really put this together, and he will introduce you together with the team of all us together. So thank you very much, and I probably hand back to Nick. Is it?
I think as we promised, that was an exceptional piece of science. And I hope what you'd appreciate as you leave tonight, what you saw from Erwin and his wonderful colleagues is, this is big picture science, right? It's not someone who comes in and uses your valuable tax pounds, euro, to do just experiments for the sake of knowledge. This is big picture stuff. It's science in the round, as you saw from the very beginning, an understanding of the economics of energy generation and the wonderful work that the team are doing. This is stuff that is fantastic, and I hope you appreciate the wonderful work that they're doing, that the group are doing, and it's a real pleasure to have Erwin sort of talking about this work. We'll take some questions. But I think it is right. It'll be great fun for you to come and see the team doing the experiments. That's not something we see very often. If you want to sort of look at Q&A sessions, go and watch BBC on a Thursday night. If you want to meet fantastic scientists doing the work and talking about the work they do, I think we want to make the most of the opportunities. But Erwin, you're happy to take a few questions, or anyone on the team? Yeah. And I think there's some roaming microphones, or I'll throw this at the relevant people. I think the team will go around. Is anyone any questions? There's one here in a second.
That was fantastic. Thank you very much. Just going back to the slides back at the beginning about the sort of the alternative chemistry department and having the sort of water and so on, it got me thinking about the fact that we've got in Cambridge, we've got a freshwater crisis already, this whole area. You're nodding, so I'm sure you know all about it. And we probably will have more of a crisis around the world with source of water. So in terms of the artificial leaf, what sort of water are you considering for supplying it?
Very important question. That's also why we have so much interest in sea and polluted water. Of course, in most of the experiments, we have shown this is fresh water, just not to complicate our systems, but we do work on polluted seawater. And actually, we have quite a nice innovative system ready and established, and will soon be published, where we can actually couple solar fuels generation with water purification. So for us, we are very interested in looking at light management. So looking at the full solar spectrum, not just using the UV part and the visible, the high energy part, but actually also using the heat. And also what already Celine hinted at, actually we do want to beat conventional systems where you just have PV coupled to an electrolyzer. And I think the way forward is heat. So how does this system work? Actually it also floats on the water, as you've seen the leaf. But it really levitates with some carbon type paper that really absorbs all the heat, actually heats up the device. And this heat then allows the water to evaporate. We take the water vapor then with the UV light to make hydrogen, and the remaining part just condenses and forms purified water. So we tackle this head on. I mean, this is again not commercial. This is just proof of principle. We are just playing. We have fun in the lab. But we look at this. We want to go much more into sustainable nexus more broadly. I mean, fuel is one compartment and of interest. But I think we need to think of it in the broadest sense. And water purification, as you mentioned, is very, very important. And if it's important in Cambridge, it will be even more important than in 80% of the world, I think.
Thank you.
Gentleman at the front. Oh, just.
If it had been a sunny day in Italy, would you have won the first prize?
Motia Virgil? No, I think possibly yes. So I mentioned the categories. There was one category that we would never win, and this was the amount of fuel. And this is because the group that did win the first prize produced a huge amount, but they made actually hydrogen and then converted the hydrogen with a methanizer with CO2 into methane. But this actually was not exactly the description of the call. It was actually meant to be direct conversion. So we do know, in fact, from correspondence that we did win, if I can say this, on the innovation categories, etc. But of course, since we did not really make sufficient fuel to demonstrate, this was really the final problem we faced. So of course, I don't know if we would have won, but I think we would have been in a good position. Yeah. And when is the next? We wait for Brussels and or some other generous agency to announce a competition. Yes.
We'll take one from the back.
Yes, hello. Maybe I missed it, but what was the reason for having to go through Europe to do the field test? Why did you all go?
Sorry, because this was an international competition, and the final was in Italy. So IPSRA, that's where the competition happened, is the European Solar Testing Facility. So it's a European site for solar energy research, and also they can do all the standardization. So we got all the spectrum of solar energy. So it was really effectively a setup where simply Europe does the testing.
Thank you.
So sorry for the waffling, but that's more or less it, yeah.
Just the lady here with a blue top, yeah.
Yes, thank you. Sorry, cheating. I've got two questions. The first one is, I don't quite understand why what you call syngas, carbon monoxide, is so useful when we all think of it as a nasty toxic gas. And the second question is, why were you sponsored by Marie Curie? What relevance does it have to cancer? I think Marie Curie is on your final slide.
Yes. So there are two questions. The first one is on carbon monoxide. So carbon monoxide, of course, for public perception is a huge problem because we have carbon monoxide sensors and we know it is a very bad gas. But actually for the chemical industry, it is very, very useful. So because carbon monoxide, well, contains carbon and it's very energy rich. So you can use carbon monoxide as an intermediate to make many different products. So one example would be to make liquid fuels from it in the form of hydrocarbons. So and it can be very safely handled in industry as well. It's an issue if it would be here, but in a reactor in chemical, it's, you know, as I mentioned before, it's in 100 megaton scale. It's being used very safely, so that there's no problem there. Marie Curie, there is from the European Union, there's a fellowship scheme that funds postdocs, like Motia, for example, and they provide funding for them to do research. And we have benefited from this European scheme very tremendously. So actually I would say from my research laboratory, I still think 2/3 has been funded from Europe, and it's actually not British money yet. And Marie Curie has been for us a phenomenal, I think we brought already 14 postdocs into the lab here funded from the European Commission on Marie Curie grants. Yeah.
Hi, thank you for that. I'm picturing a world where you're successful and hundreds of acres or square miles are covered by artificial surfaces, imitation leaves. And I'm wondering why that is a better world than plants that make fuel and all the things that you're hoping to make. What is the advantage of this artificial method?
So the artificial method should be able to produce fuel at much higher efficiency than plants can do. So with natural photosynthesis or plants, you're usually around 1% efficiency or lower, meaning the solar energy that hits the plant is being converted into a sugar. So with our devices, we are quite confident we can reach 10+%, so at least an order of magnitude more. This means, of course, the surface area also reduces proportionally. And then the other advantage is we can actually dial the product we want. If you're natural, again, the sugar is then you end up with a lot of biomass, and then the biomass is not quite useful per se. It actually needs to be processed further, so there are further efficiency losses. So our vision here is actually to make at much higher efficiency directly the product of choice. And of course, you're right, we need land use, but actually it's not as dramatic than it may seem. So if we assume we can make this 10% efficient panels, we would only need to cover 0.16% of the land surface area of the world, 0.16, to produce all the fuel and energy for the planet. And of course, we can even tap into some open water sources if we take environment, biodiversity into account. So the land area, of course, it is a lot of land, but it's still a tiny fraction of what is available.
Mine's been answered. Yeah. I wanted to know who won the first prize and how they did it, but you've answered that.
All right, just as in photovoltaics, is it possible to concentrate the sunlight with mirrors or lenses to increase the yields, or would heat management be an issue?
Yeah, that's exactly what we are doing. And we believe concentrated sunlight provides a huge advantage. I think that the one challenge for this type of technology is you need to do chemistry on a square kilometer scale. And just the supply of waste and removal of product will be quite tricky. And of course, with solar concentrated, we can also reduce the reaction space. And we really think the heat that you mentioned should be really beneficial, because we know if we increase the heat, our catalysis accelerates. So our devices should become much more efficient. So we're doing at the moment quite a lot with heat management, solar concentration. We could even give a full lecture on this to demonstrate the big advantages, as you say, of using heat to our advantage.
Two questions. First of all, what's the timescale for the commercial application of this product? And secondly, if it's a circular economy, where do the products for to make the physical artificial leaf in the first place come from? Because I assume it's not in the circular model.
Yeah. So what we have shown today, the CO2, I think, is still quite far away from a commercial product, simply because we need far more efficient, much more stable devices, much more scaling, etc. we do believe that actually the breakdown of plastic waste and biomass is much more imminent for commercialization. So in fact, we are discussing and actually very close to startup in this space. And I think there are opportunities simply because with waste breakdown, we are not only making one fuel, but actually we mitigate waste, we make the fuel, and we even convert the waste into chemicals. So the value creation is far, far higher. And even from an efficiency point of view, there are really huge advantages. So long story short, CO2, I think, only is quite tough. Connected to waste, I think, is much more imminent. On the materials, you're completely right. At the moment, our devices have a lot of components that are toxic and difficult to scale. But what we try to do next, of course, is replace these components. For us, it was just very important to finally get something that works, to demonstrate the functionality, and we need to step back and think much more broadly. I like the idea of having even students, when they come into the group, they should start thinking about recycling from day one. You know, once you have your device and it's dead, how do you recycle all the components? And that's what we have to do, but we are really at a very early stage still, so this is to come. Yeah.
Okay, well, I'm sure there are a few more questions, but maybe you can ask the team in person. I think we're going to wrap up the televising very, very quickly. Again, it shows you that 5 million euro is just a number. The team ultimately did win, we think, but they also did win intellectually because all the things that didn't quite go as they expected will produce better science. So next time we expect a lot of champagne when they do win the prize, and hopefully it'll double by the time you get there. So again, you get a sense that not only is this big picture science, but as you've met members of the group, and there are some others at the back, Erwin attracts people from all over the world, funded from sources from all over the world, which shows the impact of the work. This is not just local. The world is interested in what Erwin and his team does. In terms of the outreach stuff, I do suggest you go online and check his website. There's some fantastic stuff. Is your Lego clip still on there? Brilliant, right? I'm not going to tell you anything more. Go and watch this science described in Lego. So you can find it in the chemistry department website. Actually, you're on one of the banners having won the Hughes Prize. Go to the group, go to the links. Absolutely wonderful outreach work. So congratulations to the team for the wonderful work they do there. Ladies and gentlemen, if you can thank Erwin and his team for the fantastic science they do and for the presentation tonight.
Thank you.
And again, thank you for those who've helped us. Do come and mix and meet, look at experiments happening. And for those of you who are watching online, thanks for joining us. And again, keep in touch either via the ChemiCam, I suppose, Diane, or through the various publications that you produce. Just follow what we do in the department and join us on other events such as this. For those of you who are in the department, have a safe trip home tonight, but hang around for a while and do please come up and look at some of the experiments and meet the team. But for those of you heading off, have a safe trip home and a wonderful weekend. Okay.